Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I'm one of the co-founders here along with my younger brother AJ Raj. As you can see, there's a new Algebra II lesson I have prepared for you, and today we're going to be talking about the Fundamental Theorem of Algebra. It's going to apply a lot to the polynomials we have been discussing in previous videos. So the objective of this lesson is to use this fundamental theorem of algebra that I'm going to introduce you to in order to solve polynomial equations that have complex and real solutions. So we're going to be incorporating all our knowledge from quadratics when we learned about imaginary numbers, along with how we learn to solve for the root solutions or zeros of polynomials of pretty much any degree. We're going to combine those together so that we can find all possible roots of a polynomial. And you're probably wondering, how are we going to determine how many possible roots there are of a given polynomial? Well, that's where the fundamental theorem of algebra comes into play. And just take a look at this meme I have right here. You pretend you're a math student and you finally prove the fundamental theorem of algebra. We're not going to do any proving here, but I guess you could say that by solving these problems, you're applying the theorem and therefore showing that it's valid. So it's kind of an accomplishment because it's not very difficultly worded, but the amount of work it takes to finally apply this theorem and get to your answer is quite a bit. But you can hang in there. I believe in you, so we got this. Before I jump into the video, I would really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Let's jump into an essential understanding of what the concept is. The topic of the video is again the fundamental theorem of algebra. So what we're doing essentially in this process, this is put in pretty much layman's terms. This is not the super fancy mathematical way that the textbook puts it, but I will show you that on the next slide. But simply put, this theorem is where you're using the degree of a polynomial equation, and this degree is going to tell you how many roots the equation has. So to answer that original question, how many roots does a polynomial have? How do we figure that out? You just look at the degree of the polynomial. So you find the term of the polynomial, you put it in descending order first, of course, from the term with the highest exponent to the term with the lowest exponent, which is usually x to the 0, which is a constant term. You find the degree of the term with the highest exponent, take that degree, and whatever that power is, that's going to tell you how many roots that the polynomial has. And we'll get an understanding of that further. So it's easy to see graphically that every polynomial function of degree 1 has a single 0, the x-intercept. So if you say a polynomial of degree 1, what are we talking about? Well, the term with the highest degree, with the highest exponent is x to the power 1. X to the power 1 is x, so that's going to be a linear equation, so a line. So y equals mx plus b. Usually you'll see it in that form. You can see that when you graph this, you have a y-intercept where it touches the y-axis and crosses it, and you'll also have an x-intercept where it touches the x-axis and crosses it. With a line, this only happens once. It's not like a parabola of a quadratic function where you can cross the x-axis multiple times, more than once, so 2 times the max. It's not like that when you just have a polynomial of degree 1, so y equals mx plus b. However, there appear to be 3 possibilities for polynomials of degree 2 corresponding to the examples below. So now we're moving from that basic linear line graph that we've been talking about. Now we're moving into another unit we did, which was quadratics. And if you graph a quadratic, which is y equals x squared, that's the parent function. You can write it in 2 different forms, vertex form and standard form. But when you graph that, regardless, you're going to end up getting a parabola, which is like a U. If it's positive, then it's going to be like a U, like a bowl. If it's negative, it's going to be reflected. It's going to go downward, but it's still going to have that U shape. And when you have a parabola, there are 3 possibilities for solutions. You're not just going to automatically say, oh, this has 2 solutions. This has 1 solution because it's a quadratic. Well, depending on the properties of the graph, you can have 3 different scenarios, which you're going to see here in the image. In the first scenario, we have what we consider like a normal parabola. This is what we usually see in class, where we have 2 nice x-intercepts. Here you can see they're at x equals 2 and x equals negative 2. This is the graph of the equation y equals x squared minus 4. So this is pretty much the parent function, but we're moved down 4 units because of this minus 4. It has 2 real zeros like I just described to you because it crosses the x-axis twice. Over here, we have a different scenario. As you can see, it almost looks like the parabola is resting right on top of the x-axis. It actually does intersect the x-axis, but just once, and that is exactly at the vertex. So that's the only situation where you'll only have one solution to a parabola where the vertex is touching the x-axis. If we have the vertex down here, for example, then if we draw the parabola, it's going to intersect the x-axis twice. But if we draw the parabola up here, if we draw the vertex up here, then what happens is the parabola is never going to touch the x-axis. So in order to have exactly one real zero or one real solution, it has to be on the x-axis, and you can see that modeled with the function y equals x squared minus 2x plus 1, or the equation. And finally, we have a situation where we have no real zeros, and this pretty much means that the parabola will never touch the x-axis. It's pretty much where the parabola will open up above the x-axis or open up below the x-axis, but it'll never actually intersect the x-axis, as you can see here. And this is represented by the equation here, y equals x squared plus 2x plus 2. So it really depends on what equation you're looking at when in regards to the polynomial. So how does the fundamental theorem of algebra come into play? Well, in those two examples you saw before, you saw that there were scenarios where we didn't touch the x-axis at all, or we touched it only once. Well, that's on the real coordinate plane. But what if we had the imaginary coordinate plane? Based on the fundamental theorem of algebra, as you can see here, with the quadratic, we're supposed to have two solutions every single time based on this rule, which I'll go over. But in those last situations, we could have 2, 1, or even 0. That means that whatever isn't represented as a real solution is probably an imaginary solution. And that's where we're going to bring the concept of imaginary solutions into play with this theorem. So the theorem states that if p of x is a polynomial of degree n is greater than or equal to 1. So the degree is, remember, you take the term with the highest exponent, and whatever that exponent's value is, that is the degree of the polynomial. So if that exponent is greater than or equal to 1, so if you have a function that is linear or higher, then p of x equals 0. So p of x equals 0, this pretty much is where the function p of x, when graphed, is going to intersect the x-axis, has exactly n roots. Remember, n is equal to the degree of the polynomial. So let's say we're looking at a quadratic, y equals x squared. Well, in that case, n is equal to 2, and this has exactly n roots. So it means that this polynomial y equals x squared has exactly 2 roots, and has exactly 2 roots based on that exponent. This is going to include multiple and complex roots. So we could have multiple roots. In this case, if n is greater than 1, we are definitely going to have multiple roots. And then we're going to include complex roots. So this is going to be where we have I thrown in there. And I'll show you two examples applying this theorem. So problem number 1. What are all the roots of this long polynomial? It's to the 5th degree, and luckily it's in descending order for us. So x to the 5th minus x to the 4th minus 3x cubed plus 3x squared minus 4x plus 4 is equal to 0. So already said equal to 0 for us, and this is exactly how you would solve it. So I'll walk you through the process. So we're going to use synthetic division as we have been doing before from polynomial factoring. We're going to look at the constant term, which is the last term here, which is 4, and we're going to look at the coefficient of the leading term x to the 5th, which is 1, because 1 times x to the 5th is x to the 5th. The factors of 4 are 1, 2, and 4, and the factor of 1 is 1. By combining these factors, you're pretty much going to end up dividing these values up here, 1, 2, and 4, by 1, and we'll end up getting 1, 2, and 4 again, but we're going to count for positive or negative for each of these. And in a long-winded sense, this is in the next problem I'll show you a bit of a shortcut for this, but I wanted to show you this problem because this is really the concept. What you can do is you can try each of these values using a guess and check method, and essentially try to do synthetic division with this long polynomial here. As you can see, I set up, so the first number I did was 1. 1 is always a safe number to go with, so what we did was we pretty much just did synthetic division. So if you want, just take a second to look at what I did here. I pretty much did synthetic division. So we were looking at the factor x minus 1, because here you can see 1, so if we have the factor x minus 1, set that equal to 0, x is equal to 1. So we're doing synthetic division with 1. I rewrote this polynomial up here in terms of each term's coefficient. And then we just did synthetic division. As you can see, I did all the work here for you, so I highly suggest you just pause the video and look at the work. And then I ended up with this result. Because at the very end over here, I ended with a 0, we know that 1 is going to be a factor, so I wrote that down as a solution. And keep in mind with the fundamental theorem of algebra, because our leading terms exponent is 5, that's technically n is equal to 5, so we're supposed to have n roots. So we're supposed to have 5 roots for this. So we're looking for 4 more roots. What I did next was I took these numbers I found down here, which actually represent a polynomial, which is the quotient after we do synthetic division. I took this and then I picked another number from this series up here. So I just went up to 2. I didn't go to -1. I just went up to 2, and then I plugged 2 in. And then what I did was I did synthetic division once more. As you can see, just pause and look at the work if needed. And then I found the next polynomial. And because we end with a 0, this is also going to be a factor, so I wrote 2 up here. And then I just continued this process and repeated it with -2. I just realized over here I wrote a plus or minus 1. This should actually be a plus or minus I. So I'm really sorry about that. Make sure you write that if you're taking notes. This is supposed to be a plus or minus I. I believe I wrote an I, but it looks a lot like a 1. Just wanted to let you know. And a way we can validate this is what I did was I took the quotient after each synthetic division process. The first quotient was x to the 4th minus 3x squared minus 4, and I actually just factored this like normal, and you would get x squared minus 4 times x squared plus 1. You set that equal to 0, and if you solve each of these, you would see that this set of parentheses over here gives us x is equal to plus or minus 2, and this set of parentheses is actually going to give us plus or minus I. I would suggest you pause and just look at the work that I did, and you'll see that these are the two solutions we'll get. So these are also going to be roots. So these actually are the second, third, fourth, and fifth roots other than 1. So those would be all our 5 roots. I repeated the same process with another quotient that we got during the synthetic division process, x cubed plus 2x squared plus x plus 2. Just factored this, and then I solved, and we got x, by setting it equal to 0, and I got x equals -2 and x equals plus or minus I. So again, -2 we already found as a root in this problem, in this factoring, in this solving over here, and then we also got plus or minus I over here as well. So those are, again, it's just like certifying, yes, these are roots. And then lastly, when we did synthetic division, the last time we did synthetic division, we had x squared plus 1 equals 0 as a quotient. So then you just solve and get x equals plus or minus I. So this again proves that plus or minus I is a solution, is a root of this polynomial over here. So once again, I'm sorry about this. Plus or minus I, it's supposed to be plus or minus 1. It should be a plus or minus I. So make sure you correct that. So yeah, that's problem number 1. We'll quickly go through problem number 2. We're going to use a calculator. So what are all the zeros of the function g of x equals 2x to the 4th minus 3x cubed minus x minus 6? Well, if you look at this function, the highest term is x to the 4th. Luckily, it's in descending order for us, so it should have 4 solutions. However, as you saw in the last problem, it's pretty tedious having to do the guess and check method, because in math, especially if you're in a higher math class, you don't really like the guess and check method. You want to be certain that you got to your answer a specific way. You don't have to want to guess your way to the answer, unless it's guess and check with factoring quadratic equations. That is always a go-to. But anyway, we do the same process we did last time. So we take the constant, which is 6, we take the coefficient of the leading term, which is 2, write out their factors, and then we do a over b. In this case, 6 could be a, and then 2 would be b, and then we would divide. So 1 over 1 is 1, 1 over 2 is 1/2, and we just repeat this process as we usually do, like we did with like the rational root theorem and then the conjugate root theorem. And we repeat this process, and then we would find all possible roots that are not guaranteed, but these could be possible roots. And then what we do is you can actually graph this on a calculator. And hopefully you know how to type this into your y equals. You'd graph this, and you'd also graph the line y equals 0, which is the x-axis. Then you would view it, the graph, and then you'd find the points of intersection. And if you did that, you would find that the points of which I trust you'll do, you can pause this video and do it on your calculator and find the points of intersection. You'll find that they're -1 and 2. Well, how does this help us? Well, what we can do is when we look at this polynomial up here, the highest degree is 4. So we know that it's going to have 4 roots. In this case, we've already found 2. So we can use the 2 real roots that we've found to find the other 2 roots, which we can automatically assume are imaginary, because your graphing calculator graphs on a real coordinate plane. So what you're going to do is you're going to rewrite this polynomial up here in a synthetic division form. You're going to divide it by the x plus 1, which is a factor, which is going to be -1. If you do the polynomial division, you'll get this quotient right here, and then you're going to take this quotient and then divide 2 into it, because x equals 2 was another solution. And then you'll end up with 2, -1, 3, and 0 as your remaining numbers. If you write this in normal polynomial form, you'll get a quadratic 2x squared minus x plus 3. And what we can do here is we can actually use the quadratic formula, because you use the quadratic formula to find solutions of a quadratic. And if you use the quadratic formula, you will end up through simplification. Remember, quadratic formula, just to remind you, is -1 plus or minus the square root of b squared minus 4ac divided by 2a. If you apply that using the numbers you have here, you will get 1 plus I root 23 over 4. And actually, this should be plus or minus. Sorry if it says plus. It's supposed to be plus or minus I root 23 over 4. But I wrote 1 plus or minus I root 3 over 24. I root 1 plus I root 23 over 4. Sorry. But this is actually, if you look at it, because there's a plus or minus, this is actually two solutions in one answer. So this accounts for the third and fourth solution, which are both imaginary, and that's how you would solve. And you actually streamline the process by using your calculator to find the two real roots. Usually, if you are in Algebra 2 honors, you're expected to be able to do all of this without a calculator. So it's going to be more involved, more work, and less margin for error. But if you're using an Excel class, they will let you use a calculator for, let's say, an assessment, or this would be like a calculator section on your assessment where you are allowed to find the first roots with a calculator, the real roots. Just keep that in mind as well. Alright, that's all I have for you today. I hope you enjoyed the video. If you did, please like, subscribe, hit the post notification bell, and drop a comment down below. Please share using our socials as well, and stay tuned for the next video. Thank you, and I'll see you next time. Bye.